All right. So hopefully you had a good break. Final day. We're into kinetics. So we're just going to cover a couple more things out of kinetics, and then we'll wrap it up. I think we'll check out a lab, and that's all they wrote. So we've been talking about kinetics, and remember, kinetics is the study of how fast or slow a reaction takes place. Usually, when we talk about a rate, we're usually talking about sort of the change in the concentration over the change in time. And that gave us what we talked about last time, which was the rate expression. And the rate expression does express that if you have a reaction, we'll just do like 2A plus 4B goes to 2C. We could write a rate expression for this particular reaction. Remember that we can kind of incorporate the stoichiometry involved, and we could do that by taking the rate is equal to, remember that our reactants should be decreasing with time, which means we do use a negative here. And the negative there is for reactants only because the change in the concentration part of it should be a negative number, and those two negatives will turn our rate into a positive number, which is what a rate should be, a positive number. This would be the, let me do that right there. Maybe try that again. We're going to do 1 over our coefficient here to take into account our stoichiometry. So in this particular example here, that would be 1 over 2, change in the concentration of A over the change in time. Again, because this is decreasing with time, when you do the final concentration minus the initial concentration, as I just mentioned, that's going to yield you a negative number there. Along with this negative, we'll turn our rate into a positive number. We could also set this equal to everybody else in the equation, being negative, again, for our next reactant, 1 over the coefficient, change in the concentration of B over the change in time. And we also can do it to our reactant. Now, with our reactant, it is increasing with time, which means that we don't use the negative because the change in the concentration will actually be a positive number. And this would be just 1 over 2 change in the concentration of C over the change in time. Now, obviously, as we talked about, you can, if you need to, just pull out, ones that maybe you're interested in. So maybe let's say we had some information about A and we're interested in C, so we can write independent sort of rate expressions for each of those. And really what ties those together, so for example, let's just say we had the concentration of A kind of initial and final, and we obviously have the time as well. So we would be able to actually calculate the rate here, and that would give us the average rate for this reaction, which would be the exact same number as the rate over here. And what that would allow us to do, for example, again, is to maybe figure out how C is changing with time. It would be a positive change with time as it is increasing with time. So what this allows you to do, as we talked about, is essentially if you just know really one piece of information, either the average rate or how a reactant is changing with time or how a product's changing with time, you basically can use these relationships to figure out how everybody in the reaction is changing with time, how they're increasing or decreasing their concentration with time by really just that one piece of information that you have. We also talked about at the end there factors that affect the rate of the reaction. So concentration is a really big factor that affects the rate of a reaction. If you have a large concentration, that means it's not going to take a very long time for the reactant molecules, for example, to find each other, and that reaction probably would occur a lot faster. Things like temperature as well also plays a really big role in terms of the rate of reaction. Typically, if you increase the temperature in pretty much most reactions, that should also relate to an increase in the rate of the reaction. As we'll talk about, there's sort of a hill of energy that the reactants has to climb to get to the other side, to the product side. And by obviously increasing the temperature, increasing the energy, and that gives a lot more proportion of molecules, enough energy to get to the other side. So that's obviously plays a big role. Obviously, the opposite effects as well. If you lower the temperature, typically you will slow down the reaction because now everybody has a little bit less energy. There's less molecules that have enough energy just on their own to get up and over the hill of energy to get to the other side. So there is this sort of, as we'll see, activation energy hill that the reactants have to climb to kind of get to the other side. So increasing the temperature is directly allowing more to get to the other side, while kind of decreasing the temperature will probably allow less to get to the other side. Any questions on that stuff there? All right, so continuing on here, I kind of wrote over it, but we'll come here. This is where we left off. So what we're going to talk about now is actually the rate law, and the rate law is a equation that expresses basically the relationship of the concentration of the reactants to a certain power that will get you a particular rate. So for example here, this is what a sort of generic rate law looks like. The rate is equal to K. K is our rate constant, and we talked a little bit about that last time. It is essentially the how fast or slow the reaction's happening. It's specific for a reaction that's happening. These are the concentration of A to the X and B to the Y. The X and Y here are what are referred to as being orders, and these are the orders for each of these reactants. They are sort of, if you think about it, kind of the proportion of those molecules you need to sustain a specific rate. Um, they are not the coefficients in the balance equation. So that's one really big error that sometimes people make. They think, oh, those orders must be the coefficients in the equation, and they're not. Rate laws are found experimentally. So they're always found experimentally, which means that they are not based on the coefficients that you find in the equation, the overall rate law as well. If you add up both of those orders, if you take like X plus Y, that gives you the overall order of a reaction. And rate laws only involve reactants. So as you can see here, it is just reactants that are involved in the rate law. No products are found in the rate law, so just reactants that are there. So what does the rate law sort of help us understand? It does help us understand sort of the concentrations of everybody you need in a reaction to maintain a particular rate. Now, let's just say, for example, you were doing a reaction and it had a specific rate law, and maybe that reaction is happening too fast, or maybe it's happening too slow, and you want to sort of maybe speed up the reaction, or maybe in some cases you want to slow down the reaction. So if you kind of know the rate law for a particular reaction that you're dealing with, it does give you some helpful information about some ways that you could manipulate the rate or the experiment that you're doing to maybe slow it down. So, for example, at another school I teach at, we do kinetics experiments, and sometimes, depending on the semester, the way the reaction is set, if students are super slow kind of putting everything together and getting it into like the machine to take the readings, the reaction's over by the time they've kind of mixed them and kind of put it in the machine, and they catch nothing in terms of the reaction and go like they measure absorbance values, for example, and it's just like a flat line because the reaction is actually over before they get there. So, for example, in that situation, what they typically do is they know the rate law for the reaction we're looking at, so they can play with the reactants to slow it down, give students a little bit more time, for example, to mix them and get it into the machine and stuff like that. So, for example, if we had a rate law like the rate is equal to K times A to the first order and B to the first order, which typically you don't write with the ones, but I'll just put them in here. Just like anything in chemistry, we don't see anything on the top there. It is assumed to be 1. The overall order for this reaction, by the way, would be 1 plus 1, which is a second order reaction. Now, what does this help us? So, for example, let's just say we did this reaction and we had a concentration of A of, say, 2 molar, and B of like 2 molar. So if we were to sort of calculate the rate and put it into our rate law, the rate would equal, and I'm not going to worry too much about the K here. It's a constant, so it'll be the same number in every example. But basically, we're going to take 2 times 2, which gives us a rate of like 4 molar, and we'll put the seconds. So we have a rate that's happening in this reaction of like 4 molar seconds. So let's just say I decide, hey, in the next experiment, I want to increase my concentration of B. So I'm going to go 2 molar for A. And now for B, instead of 2 molar, I'm going to increase it to 4 molar. So I'm going to double just the concentration of B in this case. And if I put that into my rate expression here, our rate law, we'll end up with K times 2 times 4. And that's going to end up now with 8 molar seconds. And what happened by just simply doubling the concentration of B in this reaction, my rate went from 4 basically to 2. My rate also in this case also doubled, right? So I then since sped up this reaction, and I could do that by simply just increasing the concentration of B to 4 molar. By the way, I could have also increased it by increasing the concentration of A as well, and it would also increase the rate of the reaction. It would actually increase it the same sort of effect as we see here, because the orders of each of these guys are 1. So it's almost like if you double the concentration, you will see a doubling of the rate, if you triple it and so forth. Same idea, maybe this reaction is happening too fast and I really don't want to speed up the reaction, but instead I want to like slow it down. So maybe in a third experiment, I go, okay, I'm going to keep my A at 2 molar, but I'm going to drop the concentration of B to 1 molar, which was half of what I originally started with. And if I put that into my rate expression, I would end up with K times 2 times 1, which gives me 2 molar seconds. So here I cut my concentration by half, and my rate from the original one has also dropped by half. So I've now slowed this reaction down half as fast as it was moving with the other concentration. So these are one of the benefits of a rate law is if you kind of know the rate law and maybe you're doing some type of experiment and maybe you need to slow it down, speed it up, you can play with the concentrations and you can actually affect how fast the reaction is slowing. Now, the effect that you see does depend on those orders. So let's say I had a different reaction where the rate law was K, A to the first, and B to the second. So now if I just use my A as 2 molar and my B concentration as 2 molar, and I put it in there, I will get the rate is equal to K times 2, 2 squared, that is 4 times 2. That gives me 8 molar seconds. So for this reaction, I'm moving at like 8 molar seconds with those concentrations. By the way, a lot faster than I did over here, where the order for B was 1, right? Now with the order of B being 2, we see a much higher sort of initial rate than we did over there. Now let's say I did the same thing and I take my concentration of A, keep it at 2, but change my concentration of B to 4 molar. So now when I put that in there, the rate is going to equal K times 2, 4 squared. That's a lot of math. That's 16 times 2. That's 32 molar seconds. Yeah. In this particular case, my rate increased by a factor of 4, right? So it's going up 4 times. In this case, I only doubled my concentration here of B, right? And that's because in this reaction, the order of B is second order versus first order. So we're seeing a much greater increase with just a little bit, the same amount of increase in the concentration. And obviously, if I cut B as well in half to 1, we would end up with A is 2 molar, B is 1 molar, and we put it in there. That's going to give us our rate is equal to 2 times 1 squared. It's going to give me 2 molar seconds. And that also is about 4 times slower by cutting it in half. So in this case, because B has a order of 2, it is actually a greater effect on the overall rate than 1. Now I could still do the same thing with A, right? And I could change concentration of A, we would not see as big of a change, right? Because the order of A is only 1. So if you did A to the 4 there, and you doubled A but kept B constant at 2, now when we put it in there, the rate's going to equal K times 4 times 2 squared. So that's going to give me now 2 times 2 is 4 times 4 is 16 molar seconds. So we did see a doubling of the rate, but it did not go up as much. So if you needed to super speed up the reaction, you would want to, in this case, play with B's concentration. It's going to have a much greater effect on the overall rate of the reaction because it is second order versus first order for A. But if you just want like a milder sort of change in the rate, you might want to play with A's concentration. Or if you just need to slow down the reaction a little bit, A would be the one to play with because that's not going to have as big an effect as if you did something with B. Any questions on that there? Now, something else that sometimes happens is you could have a rate that is equal to K, A to the first power and B to the 0 order. And in this particular case, if I have A that is 2 molar and B that is 2 molar, when I put it into this rate law, the rate is equal to K times 2 and 2 to the 0. When you take something to the 0 order, it equals 1. Yeah, so it equals 1. So that basically equals 1. And that would give us a rate of 2 molar seconds. Now, in this particular case, because B is to the 0 order, it has absolutely like no effect on the reaction. You could like quadruple the concentration of B. It's still going to end up being 1 when you put it in there, right? When you take it to the 0 order. So it will have no effect on the overall rate. So if you want to do something in this reaction, B is not the reactant that you would want to play with because it has no effect on it. You can do whatever you want to it, which is also a benefit in case you wanted to do something and needed to increase or decrease. It won't have an effect on the rate. You would only have the approach here of having to play with A. A would be the only thing that would affect the rate. Any questions on sort of the rate law there? So that's sort of the practical aspect of the rate law and understanding that, and it can help you in sort of real life situations, either to speed up the reaction or slow it down. Any questions? Okay. So let's talk about how we actually calculate the orders. Like I said before, it is a experimental, and the rate laws are based on experimental information, which means typically speaking, when you come across a kinetics problem where you're trying to figure out the rate law, you typically are given a table like we see here, and you're typically given a table of initial concentration of your reactants and an initial rates for each of those experiments. So the first thing that you would do is just think about this reaction here and write a generic rate law, which would look something like the rate is equal to K times the concentration of F2 to the X and ClO2 to the Y. And really the goal of using this table is to figure out what the X and the Y is. And once you do that, you also are then able to really determine what is the value of the rate constant once you figure out the orders. So you could do this a couple different ways. You could look at the information and just analyze it. I find most people are probably not the best at that. So probably a more mathematical approach is probably a better move. And you could do something like this where you take rate 2 over rate 1 is equal to K A to the X and B to the Y, K A to the X and B to the Y. So what this means is it is not that you go to the table and you just take the first 2 experiments or anything like that, numbered 1 and 2. It means you want to go to the table and you want to pick out 2 experiments. And the goal here is for it to be easier on the math for you. So usually for math, to make it easy, we want just like one unknown at a time, right? We got multiple unknowns. That usually is not so easy. So when we take a look over here we could look at experiment 1 and experiment 2. The concentration of F2 stays the same, but the concentration of the ClO2 changes. And that's really what you're looking for. You want 2 entries in the table. Now, there's only 3 in this table, could be 4, 5, 6, 7, a bunch of entries. But we want 2 where one concentration stays the same and the other varies. So if we take a look at experiment 1 and 2 here, we see that happening. Now, what you're going to do is basically take experiment 1 or experiment 2, put it on the top, and then the other one on the bottom. The best way to do this usually is to look at the rates, and usually what you want to do is put the one with the larger rate up on top. You don't necessarily have to do that, but if you put the larger rate up on top, usually you'll end up with prettier whole numbers to deal with rather than decimal type numbers and stuff like that. So it's a little bit easier. It doesn't necessarily have to go that way. You can do it the other. So for me, number 2 there looks like the bigger rate. So what I'm going to do is up on top, I'm going to put experiment 2, and that is my rate for experiment 2, which is not that, 4.8 times 10 to the minus 3 is going to equal, and I'm going to put everything in experiment 2 up on top, K times the concentration of F2, which is 0.1 to the X, and 0.04 to the Y. So everything up here is all from experiment 2 from the table, and we just put it into our little equation. Now what we're going to do on the bottom there is put everything from experiment 1 in the table. That's going to be 1.2 times 10 to the minus 3, K, 0.1 to the X, 0.01 to the Y, and this is all experiment 1. Yeah. All right, so at this point, we're just going to kind of solve. When you divide on this side, you get a 4. Now, coming to this side, that is the rate constant, and that is the rate constant. Although I do not know what the rate constant value is at this point, since it is a constant number, those numbers should be the exact same number. So although I don't know what it is, since it's a rate constant, constant means same number. Although I don't know what it is, I do know they should be the same number, and they should really cancel out for this reaction. Also, because this is the same reaction, although I do not know what the X order is at this point, I do know that it should be the same number on top and bottom, which means technically these guys will also cancel out. Now I come to my Y and I divide it, and now I see I end up with 4 to the Y. And now you can solve for what Y is. You could probably just see it. Y in this case equals 1. In this case, we got a really pretty number right on both sides, 4 on each side. If you don't have nice, perfect numbers, or you did it reverse where you kind of had decimals and stuff like that, one way you could solve this, take the natural log of both sides and divide. So you could take the natural log of 4, that will bring the Y to the bottom, divide both sides by the natural log of 4, equals 1. So if you don't have really sort of nice numbers or you can't really visualize it, take the natural log of both sides and then divide it out, and that will get you what you're missing for. First up, any questions on that? So that tells us in this reaction, the order with respect to the ClO2 is going to be first order. Now that we did that one, what we're going to do is come back to our table. And the first time around, we held the F2 constant with the same numbers. Now we're going to hold this one constant. Now, when we come and look at this table, looks like we only have one option here. That is experiment 1 and experiment 3. That is where that guy is held constant. So we're going to look at experiment 1 and 3 now to figure out our other order. And once again, looking at experiment 1 and experiment 3, I can see that experiment 3 has the larger order. So I'm going to put everything from experiment 3 up on top. So again, I'm just going to go straight across. 2.4 times 10 to the minus 3 is equal to K, 0.2 to the X, and 0.1 to the Y. That again is everything from experiment 3 up on top. Now for the experiment 1, we're going to put that on the bottom, and that's going to be 1.2 times 10 to the minus 3. That's going to be K, 0.1 to the X, and 0.01 to the Y. So once again, everything down here, experiment 1, everything up on top, experiment 3. All right, we're going to do the same math. So when we divide these two, we get a 2. Once again, our rate constant on top and bottom will be the same. We know that this guy is going to completely cancel since we already figured out its order and we held it constant. So when we divide this, we're going to get a 2 to the x. That means, again, in this case, x is actually going to be 1, or first order. So that tells us with relationship to F2, the order is first order. With relationship to ClO2, it is also first order. So we can now actually write our completed rate law now that we know the orders. And now that we know the orders here, let's take this one here. The rate law would be the rate is equal to K times F2 to the first order and ClO2 to the first order. Much like most things in chemistry, if it's 1, we typically don't write it. So if there's nothing up there on the top, you could assume it is first order for each of them. And the overall order of this reaction would be 1 plus 1, which is second order, and that is adding both the X and the Y together gives you a second order reaction overall. Very common types of reactions in kinetics: zero order, first order, and second order. And that is, if you just think about most reactions that you probably have seen in equations, you typically see very commonly one reactant, maybe 2 reactants, maybe 3 reactants. You typically don't see reactions with like 4 or 5 reactants happening all at once, which would probably be necessary to get a really giant order of a reaction. So very commonly, if you have 1 reactant, maybe it's first order or zero order. Maybe you have 2 reactants, whereas maybe first order or second order. So those are very common types of overall orders for reactions that we end up with. And again, to get kind of really big ones, you might need a lot of reactants reacting. First off, any questions on how to figure out the orders here? Now that we did figure out the orders, we can then use the table to actually figure out the value of the rate constant. So we could actually take our completed rate law now, and we could put it in and solve for the rate constant, which is K. And if I did that here, K would equal the rate divided by the concentration of F2 and the concentration of ClO2. And that is just rearranging this rate law that we just solved for. Where do I get those numbers from? Frankly, I get it from the table. So you could choose any entry you want. You could choose the first entry, the second entry, the third entry, and you can put those values into this reaction or formula here, and it will give you the value of the rate constant. The only thing you can't do is mix and match. So you got to use all one's information, all two's information, all three's information. So I'm just going to take number 1's information and put it back in, and that will give me the K is equal to 1.2 times 10 to the minus 3 molar seconds divided by the concentration of F2, which was 0.1 molar, times the concentration of ClO2, which was 0.01 molar in this case. And if I put all that into my calculator here, 1.2 to the minus 3 divided by 0.1, whoops, come here, 1.2 to the minus 3 divided by 0.1, and then divided by 0.01, that is going to give me a rate constant of 1.2. In terms of the units, molarity on top and one of the molarities on the bottom will actually cancel out, and that will give you 1 over molar seconds as the units here. And that is common units for a second order reaction in terms of the rate constant. And one of the things in kinetics that you can determine a lot of times is what order of a reaction you're dealing with based on the units that you see for the rate constant. So if you see something like that, 1 over molar seconds, 1 over molar minutes, or something like that, that tells you a second order. Also, if you count the letters, those are 2 letters. Second order is typically what happens on that situation. Any questions on that there? So this is a very common way in which you can kind of determine the rate law experimentally. Take the experimental information, which is usually given to you in a table. And again, you want to keep one constant and vary the other concentration. You want to figure out the orders first. Once you have the orders, you then could go back in and figure out the value of the rate constant. Any questions on that there? So as we saw there, the rate laws are always determined experimentally. It's always in terms of the reactants, no products in a rate law. And again, the coefficient in the balance equation is not the order. As you can see in this example, the coefficient was a 2, but the order here was actually a 1, our first order. All right. So why don't you try this one here? Why don't you figure out what the rate law is and the orders for everybody and the value of the rate constant using this information here. All right, let's take a look, see how we're doing. So again, the goal here is to first figure out X and Y. Here's our sort of generic rate law. Again, only the reactants are involved. And we're going to choose two experiments here from our table where one of them, the concentrations stay the same, the other one varies. So again, we can see 1 and 2. We'll keep this guy constant and vary the I minus. So let's take a look at experiments 1 and 2 here. And again, I'm going to take the larger rate and put that guy up on top. So for this experiment, 1 is going to go up on top, and that's going to be 2.2 times 10 to the minus 4 is equal to k times my 0.08 to the x and my 0.034 to the y. And again, that's just everything from the table from experiment 1. We're going to do the exact same thing here for experiment 2 and put it on the bottom. 1.1 times 10 to the minus 4 our k, our 0.08 to the x, and our 0.017 to the y. Once again here, we're going to start doing some dividing, so that's going to give us a 2. Rate constant on top and bottom, once again, will cancel each other out, even though we don't really know what it is at this point. We do know it should be the same number. We do not again know what the x's are, but should be the same number, which means ultimately these guys should cancel out. And that's just going to leave us this over here, which should give us a 2 to the y. So in this case, y would equal 1. So the order with respect to I minus is going to be first order in this reaction. We will then go back to our table and we're going to find 2 different entries. This time we're going to keep the I minus constant, and your only options looks like experiment 2 and 3 to do that. So that is the only place where they are constant. So taking a look at, go here maybe, experiment 2 and 3. Experiment 3 looks like the larger number on the rate, so I'm going to put that up on top. And again, I'm just doing that to give me probably a better shot at some whole numbers than decimals. But if you do it the opposite way, it should still work out the same in the end. We're then going to put everything from experiment 2 on the bottom. That's going to be 1.1 times 10 to the minus 4, k, 0.08 to the x, and 0.017 to the y. That is going to give me a 4. Again, the k's are going to cancel. We already know what the y is, but this should definitely cancel. And that's going to give me a 2 to the x in this case. In this case, x would equal 2. 2 times 2 squared is 4. Yeah. Again, you can take the natural log of both sides and divide it. So that means the order with respect to our first reactant here is going to be second order. That means our completed rate law looks something like the rate is equal to k S2082 minus squared and I minus to the first. That means the overall order in this case is second order plus first order. It gives us a third order reaction that's happening. Any questions on that there? Now, once we have the orders, we can rearrange our rate law and solve for k. And if we do that, K will equal the rate divided by the concentration of S2082 minus squared and I minus. And once again, here you could choose any of the entries in the table. They all should give you the same value. I'll just go with experiment 1, and that will give me 2.2 times 10 to the minus 4 molar seconds divided by my 0.08 molar squared and my 0.034 molar. One of the molars on top and bottom will cancel, and we'll end up with 2.2 to the minus 4 divided by 0.08 squared divided by 0.034. Going to get me a 1.01. And as I mentioned before, molarity on top and bottom cancel. Still a molarity squared on the bottom and also a second. So 1 over molar squared second. Dare I count all the letters there? 2 M's and an S. That's 3. Third order, yes, first order reaction based on the rate constant there. Any questions on how to, again, determine the orders or the value of the rate constant? All right. I think we'll get through this. So now we're going to talk about specific orders of reactions and some important sort of formulas that go with it. And probably one of the most important ones is first order. And first order reactions have a reactant that goes to a product. It has a rate expression of negative change of concentration of A over time and a rate law of the rate is equal to K times A. If you rearrange and solve for the value of the K in terms of its units, you will end up with these units here. And these units here are typically the units associated with a first order reaction, and that is 1 over seconds or reciprocal seconds. It actually does not need to be seconds. It can actually be any unit of time. So 1 over a unit of time be 1 over minutes, 1 over hours, 1 over days, years, whatever it may be. Why is first order really important? It is because you're going to see it again if you are taking 200B. It is how all radioactive decay follows first order kinetics, and you will do some nuclear chemistry in that chapter, so it all follows this. Now, in kinetics, they're very big on graphs and graphs that go with certain orders of reactions. And this is one graph that you sometimes will see for first order. Not a lot, but if you graph the concentration of the reactant versus time, what you would see is what you might expect, as we talked about. As time goes on, we see a decrease in the concentration of the reactant, basically, right? As it's making products, its concentration should go down. And that brings us to this formula here on the right, which is the natural log of A is equal to the natural log of A naught minus KT. This is what is sometimes referred to as the integrated rate law. It is the rate law that helps you determine if you know some concentrations, how much time it would take for those concentrations to reach each other, or if you know the time, what concentration you should have left. This is like your final concentration. This is like your initial concentration. This is your rate constant. And this is time, so not temperature. So a little lowercase t there is actually time. Now, there is a graph that is a linear relationship from this equation, and that is the graph that we see here, the natural log of A on the Y and the time on the X. That will actually give you a linear relationship. If you take this integrated rate law and rewrite it like this, which is a very popular thing done in kinetics, because they like a lot of graphs in kinetics. So if you rewrite that integrated rate law, this is in the form of everybody's favorite formula, which is y is equal to mx plus b, right? The formula for a straight line. And that is why that graph on the y is the natural log of a. That is why the graph on the x there is time. And that should give you a linear relationship. And as you can see here, you do get a linear line. It is actually a negatively sloping line, which means the slope of that line is equal to negative of the rate constant, because the slope itself should be negative, and if it's equal to negative of a negative, will turn your rate constant into a positive number, which is what it should be. So that is what the slope is equal to, negative of the rate constant. And that is the very typical graph that you have for first order. There is also a half-life equation for first order, which is the natural log of 2 divided by the rate constant. That is 0.693 divided by k. The half-life is pretty much what it kind of sounds like. It is the time it takes for half of whatever you started with to go away. So obviously, if you started with 10, first half-life you'll have 5, second one you'll have 2.5, and after that I might need a calculator to continue on that, but keep dividing by 2, and that'll give you your half-life. The half-life for a first-order reaction is only dependent on the rate constant, it is not dependent on the initial concentration. So typically, and again, you will see these formulas again when you do nuclear chemistry in 200B if you are taking it. So usually you want to know the units associated with the rate constant, you want to know the graph, the integrated rate law, and the half-life equation. Those are four kind of important things as well. Knowing the units of the rate constant is important because it does tell you what type of reaction you're dealing with so that you can choose sort of the correct formula to use. And I will say a lot of times in kinetics problems, they don't with like flashing lights go, hey, we're doing a first order reaction or anything like that. What they will give you is the actual rate constant, and they expect you to know based on the units that you are dealing, for example, with a first order reaction. So let's take a look at how we could use that integrated rate law here. If this reaction is first order with A and has a rate constant of 2.8 times 10 to the minus 2 reciprocal seconds, how long will it take for the concentration to go from 0.88 molar to 0.14 molar? First off, if it didn't tell me like it did here that this was first order, I would 100% know it's first order because when I look at the units of the rate constant, I see reciprocal seconds. So because the K is 2.8 times 10 to the minus 2 reciprocal seconds, that unit tells me it's first order, even though it did tell me that obviously here. By the way, when we talk about the rate constant, as we did, I think last time, it is a lowercase k, as the capital K is actually the equilibrium constant, with something different. So because it is first order, I know I should roll with my first order integrated rate law, which is this, minus my KT. So I have my K. I am looking for the time, and I am taking an initial concentration of 0.88 molar and a final concentration of 0.14 molar. So I really have everything that I need to put into my equation here. So if I put it into my equation, I'm going to get the natural log of my final concentration, 0.14, is equal to the natural log of my initial concentration, 0.88, minus my K, which is 2.8 times 10 to the minus 2 reciprocal seconds, and my time here. Now, to do this mathematically, I would grab your calculator and do the natural log of 0.14 and hit equals, and then you're going to subtract the natural log of 0.88 to the other side. And then you're going to subtract it by the natural log of 0.88, and that's going to give me a negative 1.83828 is equal to a negative 2.8 times 10 to the minus 2 reciprocal seconds, and my time. At this point, I'm going to divide this to the other side. And if I do that, don't forget the negative comes with that. I'm going to get a t, or a time, that is equal to about 66 seconds. And the units would come from here as I divide it to the other side. The 1 over seconds flips to the right way and now becomes seconds as you do it there. So basically, this would take 66 seconds for that concentration to drop from 0.88 to 0.14, so just over a minute there, and we'll actually drop the concentration that low. Any questions on that there? Now, a couple of things with the first order one and all these sort of rate laws and integrated rate laws. You do always want to be careful with these two guys. They both have a unit of time in it, and you want to make sure they're the same time. So sometimes you may have like a half-life that's in like days and one that's like in weeks, and you want to make sure always that the time units there are always the same. And that's a common sort of place that sometimes people will mess up on. Any questions on that there? There's our half-life there that we just talked about for first order. All right, so why don't you try this one here? This reaction is first order rate constant of 2.9 times 10 to the minus 4. Find what was the concentration of S2Cl2 after 865 seconds has passed. All right, so let's take a look. Again, they do tell us it's first order. If they didn't, once again, I would know that from the value of the rate constant units, which is reciprocal seconds. So again, we do have a first order reaction happening. I definitely know that based on those units. That is first order. Again, we're going to use our same sort of first order equations. Although we don't need the half-life here as nothing is mentioned about it. A lot of times you do need the half-life to use with the other equation as well. But here we could just kind of use this one. And we are looking for kind of our final concentration. We're looking for that. And we have our initial concentration here of 0.0225. I'm just going to write A instead of the whole thing. And we do have the time here of 865 seconds. So putting our values in here, we're going to be looking for our final concentration, our initial 0.0225, minus our rate constant of 2.9 times 10 to the minus 4 reciprocal seconds, and our time, which is 865 seconds. This was what I was talking about a second ago. We're okay in this case. Both of the time units here are both in seconds. But again, if one was minutes and one was seconds, you would need to do a conversion on it. We could actually clean up the right-hand side there. So we're going to go natural log of 0.0225, hit equals, minus, open a parentheses, 2.9 to the minus 4 times 865. Going to get us a natural log of A is equal to negative 4.045. To get rid of the natural log, you need to take the E of both sides there. That E will get rid of the natural log on your calculator, usually above the natural log button. And that will get us here 0.0, and we'll call it 18 molar in this case. Or 175 would be good. And it is decreasing, which is good, right? We started at 0.02, we're down to 0.018. So definitely it's going down. If you did it and you went up, that probably meant you screwed up somewhere there on the calculation. Yeah. Any questions on that one there? All right, let's see. That's good. I'm not going to go too much into the other orders, but just to show you, there are second order reactions, as I talked about, which are very common. And again, you can really achieve a second order reaction by having one reactant that is second order. You can have two reactants where they're each first order. You can also have two reactants where one is second order, one's zero order. So there's different ways that you could get to a second order reaction. The units for the rate constant for a second order reaction is different than what you see for a first. It is 1 over molar seconds as opposed to 1 over seconds. Also, there's a different integrated rate law. It is 1 over the final concentration equals 1 over the initial concentration plus KT. And if you rearrange that and write it as so, that will give you the straight line version of it. And that is y is equal to mx plus b. That is why we see our graph here is a little different. On the y is 1 over the concentration. On the x is time, yielding us a straight line where the slope will actually equal the rate constant in this case. U actually is the only one that where you'll get kind of like a positive sloping line heading in the positive direction. You could also see it has a much different half-life equation as well. It is 1 over K times the initial concentration. So the half-life of a second order reaction is actually dependent on the initial concentration, and it can have an effect on the half-life as well. So those are common second order. The third sort of common reaction is a zero order reaction, and with a zero order reaction, you will have a rate constant that has the same units as the rate, which is molar over seconds. So if you have molar over seconds for your rate constant, it's zero order. If you have 1 over molar seconds, it's second order. If you have 1 over seconds, it's first order. It has an integrated rate law, which looks exactly like the first order, except there is no natural logging happening here. So this is just the concentration, the final concentration, and we could also rearrange this and write it in our straight line. Y is equal to mx plus b. So our linear graph here is the concentration versus time, and yields you that linear line where the slope's actually equal to negative k, because again, we have a negatively sloping line. You could also see that the half-life equation does deal with the initial concentration as well. So those are probably the three most common orders of reactions that you come across: first, second, or zero. And depending on what the order is, you would want to use the appropriate equation. As I mentioned before, you most likely will see first order again in nuclear chemistry if you take 200B. Here's just a nice little table that summarizes all those formulas here. Let's talk a little bit about temperature dependency on reaction rate to finish it up here. These are two energy diagrams. One on the left is exothermic, one on the right is endothermic. And this is our reactants, and this is our products. And we know that this is exothermic because our reactants are higher in energy than our products. So the only way for those guys to get down there is to give off energy. And exothermic means it releases energy. So that is a exothermic diagram. If you take the difference between where the reactants are and the products, that is what is known as your delta H. And your delta H for that reaction is the change in enthalpy. Kind of like the delta H we use for bond energy in that chapter. And a reminder that if the delta H is negative, it is exothermic. If the delta H is positive, it is endothermic. And that is what you would get here, because to calculate the delta H, you take the delta H of your products minus the delta H of your reactants. So my products are a smaller number, so you're going to take a smaller number minus my larger energy number there, and that's going to yield you a negative number when it's all said and done based on the energy that is there. As opposed to over here on the right, this is an endothermic reaction diagram. Reactants are lower in energy than the products, so the only way for the reactants to get up there is you have to put energy in, which is the definition of endothermic, is absorbing energy. And again, if you take the difference between the products and the reactants, that again will give you your delta H, which will be a positive number here for the same reason, because the products are higher, so that's going to be a larger number minus a smaller number, and that's going to yield you a positive number when it's all said and done. As you know, in a chemical reaction, the only thing that happens is you start to break bonds and you make new bonds, which means as the reactants come up this hill of energy, we are breaking bonds and making bonds. And this hill of energy from where the reactants is to the very top of the energy is what is known as the E of A. That is the activation energy. That's the minimum amount of energy that's required for a reaction to take place. That is the hill I was talking about earlier that the reactants has to climb to get to the other side. And that is why, for example, when you increase the temperature, a lot more reactants have enough energy to get up and over to the other side to make products, and that usually speeds up your reaction. When you lower the temperature, not as many people could climb the hill at low energy to get to the other side, and that slows down your reaction. At the very top is what is referred to as the transition state. That is the top of energy. And as you hopefully know in chemistry, things in high energy are not very stable. They do not like to be around there very much. And this is like an intermediate at that point. This was sometimes referred to as the transition state complex. It has partially made bonds and partially broken bonds, super unstable, and very quickly will kind of drop down the hill to make products. And you can see over here, here's our reactants on our endothermic, a much bigger hill to climb, right, to get to the other side. And that is our activation energy hill. Same thing here at the transition state. This is partially made bonds and broken bonds. Will kind of quickly drop to the other side. The actual activation energy hill plays a really big role in terms of reaction rates. The bigger the activation energy, the slower the reaction, right? A lot more energy is needed to get to the other side. Typically, it's going to take longer to do so. If you add a catalyst, which is not a reactant nor a product, it typically can speed up the reaction by finding an alternative pathway for that reaction to take place. And what it ultimately does is it actually will lower the activation energy. So if you have a catalyst you add to your reaction to speed it up, by finding that more sort of efficient way for that reaction to take place, it essentially will lower the energy hill, and that will allow more reactants to get to the other side quicker, and that is what typically will speed up the chemical reaction. There is an equation that relates to this, and that is what is known as the Arrhenius equation. K2 over K1 is equal to E of A over R, 1 over the initial temperature minus 1 over the final temperature. And these are rate constants at two different temperatures. That is your R value, which, by the way, is the 8.314 version of it, the one that has energy. That's your activation energy. And these are your temperature at Kelvin. And that is the equation that you could actually calculate something like what is the activation energy for a reaction if you know two rate constants and some temperatures that go on there. So the temperature plays an important role in terms of the rate of the reaction. And like I said earlier, typically if you increase the rate by increasing temperature, and also if you throw everything on ice, it will slow everybody down by decreasing the temperature. The goal here is to get to the other side, and the activation energy is the kind of hill that prevents or people to get to the other side and has to be conquered. In order for a reaction to actually take place, two things has to happen. There has to be a collision. They actually have to hit each other, and they actually have to hit each other in the right spot. If they don't hit each other in the right spot, you're not going to form any products. But they also have to hit each other with the right amount of energy, which is that activation energy to get to the other side. So not all collisions when things come together will actually form products. Those two things has to happen. Any questions on that there? That is the end of 200A for this.